All right, so in this question, we are supposed to answer these questions. We're going to take this rational function and find the domain, the y-intercepts, x-intercepts, x-value, vertical asymptote, horizontal asymptote, and oblique asymptote if there are any. So there's a lot of things going on in this question. All right, the first thing is the domain. Now, whenever it comes to rational functions, it means that there are variables in the denominator, and that therefore means there's some danger of plugging in an x value that would create 0 in the denominator and then result in an undefined result. So what we want to do is figure out which values of x would make the whole denominator 0 out and exclude those from the list of valid input values. In other words, from the list from the domain. Right? The domain is the list of all the valid values of x that we could plug into the function and get a defined answer. So anything undefined or anything that would make the function undefined should not be included in the domain. So what we will want to do then is take the the whole function in the denominator and solve for x after setting it equal to 0. Because in other words, we don't want to let the denominator equal 0. All right, so it's kind of like solving for 0, but in a way it's solving for not allowing it to equal 0. So we want to find out where it's going to equal 0. Okay, so really technically I should write it like this, but again, it's a restriction. We don't want to allow the denominator to equal 0. Okay, so this will help us search out those values that would create that result. Okay, and it's a quadratic with a lead coefficient of 1, so we might be able to factor this into two linear binomials. And if I want a product, two factors that give a product of -14, but a sum of -5, then I could try -7 and +2. Okay, and that will work great. And then using the zero factor property, either one of these factors, if they were to equal 0, would make the whole thing equal 0. So we want to set each one equal to 0 and then solve for x. So we'll do that. Okay, so then x equaling 7 would make the denominator 0, and x equaling -2 would make the denominator 0. So long story short, the domain should start at -infinity to up to -2, but not include it, then pick up again on the other side of -2, go as far as 7, but not include it, pick up at the other side of 7, and continue on towards infinity. All right, so we'll just go ahead and enter that here. I'm going to use my interval options from -infinity, comma, -2. Then use my union symbol, pick up with -2 up to 7, +7, which would be our next break. And then again, a union, jump over 7, pick up on the other side, and we're good to go from there towards +infinity. So that's the first part of this. All right, now we're going to go on and find y-intercepts. So the y-intercepts, well, do you realize what a y-intercept is? That's where the function will cross the y-axis. And if you recall, everywhere on the y-axis actually, actually the y-axis has an equation. It is that x is 0. Okay, that would give us the vertical line that represents the y-axis. So that means to find the y-intercept, all we need to do is plug in 0 for x into the function and figure out what the y value is. And remember that f of x, that notation f of x is interchangeable with the variable y. Okay, and so taking my function and just replacing anywhere that I see an x with 0, I will be able to evaluate this pretty quickly. And you're going to notice that all the terms in the top are going to 0 out. So the whole thing just becomes 0. So the only y-intercept is actually at the origin, where both the x value and the y value are 0. Okay. All right, so next, the x-intercepts, where are they? Well, just like the x-axis has the equation x equals 0, I meant to say, sorry, I said that backwards. Just like the y-axis has the equation x equals 0, it's true that the x-axis has the equation y equals 0. So everywhere on the x-axis, y is always equal to 0. So when we're finding x-intercepts, we always are looking for coordinates that have some x value, and we're looking for that, but we know that the y value is going to be 0. So again, we want to take our function, replace the f of x with y, and then replace the y with 0. Okay, and then once we have replaced the y with 0, we want to solve for x. Now, here's the thing though, because if the top ever equals 0, the whole thing will become 0, we actually can ignore the denominator, aside from the fact that we don't want to allow any values that are not in the domain. And we've already figured out, and I'm going to put a note up at the top just to remind us, we already said that x cannot be equal to -2 and it cannot be equal to +7. So when I go and solve for x, just as long as I don't have an answer of -2 or 7, everything else is good. So I can ignore the denominator, just focus on the top of the rational function, the numerator, and solve that for 0. Okay, now, um, because there's an x in every single term, I'm going to go ahead and factor out the GCF, the greatest common factor. And this is very helpful because now I have one linear term, okay, that I can set equal to 0, but I also can factor out the quadratic factor into two linears, hopefully. If I can't factor them, then I can still use the quadratic formula. So I'm going to see if this factors. Okay, so 1 times 2 is the only way to get a product of +2. Now it could be +1 times +2, or it could be -1 times -2. And here it should be -1 times -2, because that would give me a positive product, but give me the negative sum -3. Okay, so then now that I've factored everything out, I can use the zero product property. Set each factor equal to 0 and solve for x to find all the places that all the x values where the whole function will be 0, or where the y coordinate will be 0. So I'm going to have x-intercepts at, I'm going to list my ordered pairs of each of my points here. So at the origin, then at 1 for x, and then at 2 for x. Okay, now, are there any holes? Okay, so that's a weird question, right? Well, we already determined that there are some restrictions on the domain, right? That there are these little jumps, these union things represent gaps in where the function can go. And we typically call those, they're usually asymptotes, where what I mean is, if we graph this thing, actually, let me show you a graph of it. Okay, here's the graph of our function right here. Now, the idea is that by answering the questions in our homework question and our exercise, we would be able to figure out enough information to sketch the rational function without having to use a graphing utility like this. But for the purposes of instruction, it's helpful for me to be able to show you what it means when a rational function has gaps in its domain. For instance, we already figured out that x should not be allowed to be equal to -2. So let's look at what happens when x equals -2. We have this equation, and I'm going to change this to, no, it's right there. the blue, you see the blue? I'm going to just zoom in. Okay, you can see that it's creating a vertical line and that the function, which is in green, especially if we come up, if we look down here, right here, it's a little easier to tell that the function is avoiding this line, right? It stays on either side of that line because it really can't go there because the function is literally undefined, almost like you can't draw it. You can't define it. You can't write it down. You can't have the function showing up anywhere on that vertical line because everywhere on that vertical line, the x value is -2, and we figured out that if we plugged in -2 to the denominator, it would make the whole denominator 0, and you can't divide by 0, right? Another thing is we said that the equation, the function cannot ever have x values that are equal to +7. So here's the red line showing that vertical boundary, basically. And I'll zoom in right in here. Okay, so you can see the function, the green part, is avoiding that red line down here as well. Okay, so it goes very close to it. And, you know, if we follow this graph down further, it at one point looks like it merges with the green, but if you keep zooming in, you'll find that it doesn't. It never actually touches. It gets closer and infinitely closer and closer to the function or to that line, but it won't ever actually touch it or cross it. Okay, so that's what we call an asymptote, these vertical lines that are created by a gap in the domain. Okay, so when we figured out what the domain was, we figured out that we had vertical asymptotes at x equals -2 and x equals +7, right? Now, sometimes your rational function, since it can be factored, some of the linear factors might cancel out. And when that happens, we don't call it an asymptote like a whole vertical line. We just have a gap in the actual drawing of the function, and we call it a hole. All right, so let me show you what happens if we factor out both the top and the bottom of our function. Okay, and let's see if there are any holes, because if any of the factors are the same on top and bottom, that will create a hole in our function. All right, so I have x cubed. We already figured out how to factor this one, right? When we when we were looking for x-intercepts, we found that it was x times x minus 1 times x minus 2 is the factors that would simplify to the top polynomial there. So x times x minus 1 times x minus 2. So I'm just factoring out the top of my function, my original function right here. Okay, just factored that out. Now I'm going to factor out the bottom if I can. And we did that earlier as well. Remember when we were trying to discover where the domain issues were? We figured out that the denominator factored out to x minus 7 times x plus 2. So I'm going to write that x minus 7 times x, that none of the factors in the top are identical with the factors in the bottom. So there's nothing for me to cancel out. If any of these had canceled out, then we could have a hole, but we don't have that here. So this should be DNE, does not exist, no holes. Okay, but now what about horizontal asymptotes and oblique asymptotes? Okay, now rational functions will have one or the other, either a horizontal asymptote, so a horizontal line where the function usually doesn't cross, although it can. The oblique asymptote is a slanted. Oblique means slanted. Okay, but you'll have one or the other. Now, how do we know? Okay, so let me open up a place in the textbook that helps us visualize or refer to the information we need here. All right, so here is in the textbook, in the OpenStax textbook, where we have the information that is going to help guide us in figuring out either our horizontal asymptote or our oblique asymptote, because remember, it's always one or the other. All right, so notice that it says the horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and the denominator. And then there's 3 different bullets here, 3 different cases. and it's split up by the degree of the numerator compared with the degree of the denominator, right? Of my numerator here is 3, and the degree of my denominator is 2. And since 3 minus 2 equals 1, then there's an oblique or slanted asymptote. Okay, now we know that slanted lines follow y equals mx plus b. Okay, so our asymptote is going to be in that form, but what we have to do is some division. We have to take this function and treat it like a division problem, and then just whatever result we get, we ignore the remainder. So I'm going to be dividing. I'm going to be doing some long division here. Okay, so we want to divide x squared minus 5x minus 14 into x cubed minus 3x squared plus 2x. And we're going to be looking at the first term in our divisor, and we're going to see how many times it goes into the first term of our dividend. So x cubed divided by x squared goes in evenly x times, and then we distribute the x to each of the terms in the divisor. So we'll get x cubed minus 5x squared minus 14x. And then since we want to be subtracting this entire quantity, we're going to need to change all the signs of all the terms there in that line. So I'm going to just change from a positive x cubed to a negative x cubed, from a negative 5x squared to a positive 5x squared, and from a negative 14x to a positive 14x. Then combine like terms from the two lines there. So x cubed minus x cubed becomes 0x cubed. Negative 3x squared plus 5x squared is 2x squared. Positive 2x and positive 14x is 16x. And now we repeat the cycle that we did previously, but now we're looking at x squared going into 2x squared. So x squared dividing into 2x squared would go in 2 times. Okay, and then I'm going to do the same thing I did before. I'm going to distribute the positive 2 to all the terms in my divisor. So I end up with 2x squared minus 10x and minus 28. Okay, then I'm going to want to subtract. So I'm going to have to change all the signs of all my terms. So I'm just changing all the signs of all my terms and then combine like terms. So 2x squared minus 2x squared cancels to 0x squared. Positive 16x plus 10x is 26x. And then I have plus 28. And at this point, the degree of the first term in my divisor, or the power on my x there, is greater than the highest power of x on what I have here in my remainder. So I can't really continue from here. And this is my linear up here. This is my linear y equals mx plus b, part of the equation that I need for my slant asymptote. Excuse me. All right, so here we say there is no horizontal asymptote because instead we have the oblique or slant asymptote at y equals x plus 2. And it already has the y equals. That's why I'm getting a red error here. So I just need to get rid of the y there in my answer.